Welcome to our second video on the ESM-2 models. In the last video, we looked at the ESM-2 model architectures and training. In this video, we will look at how to use and fine-tune the models in Python. All code that you see in this video and all required packages will be available on GitHub. You will find the link in the video description. So let's have a look at the code. At the end of this video, I will show you how to fine-tune the ESM-2 model, but we will first use the pre-trained ESM-2 model to compute protein embeddings. We want to have a single embedding for each protein. We first load the packages torch and ESM, and in the variable device, we store whether we use a CUDA GPU or a CPU. Then we load the actual model. And as you can see, we load the smallest model with only 8 million learnable parameters and 6 encoder layers. I use the smallest model because I'm running the code on my laptop. At the end of this line, you also see the comment for loading the larger and most commonly used model with 650 million learnable parameters. When you load these models for the first time, their weights get downloaded from the internet, and hence loading the models for the first time can take quite a few minutes. When you load the models again, it will be much faster. In the variable last layer, we get the number of encoder layers. So in our case, this will be equal to 6. Then we load the batch converter, which we need to convert an amino acid sequence into a sequence of token IDs. We run the model in evaluation mode because at first we only want to use the pre-trained ESM-2 model to get a fixed representation for each protein amino acid sequence. And later, I will also show you how to fine-tune the model to generate task-specific embeddings. Here, we run the code and output the ESM-2 vocabulary, which is stored as a dictionary mapping the individual strings to token IDs. In the beginning, we see a few special tokens, like the classification token mapped to ID 0 and the end of sequence token mapped to token ID 2. And we see all of our amino acids mapped to different token IDs. Now we need to convert an input amino acid sequence into token IDs, so we can give our amino acid sequence as the input to the ESM-2 model. As the input sequence, we have here as an example a very short sequence, MKTGK. And we need to store input amino acid sequences in a list. The list contains of tuples or consists tuples, where the first entry is an identifier or name of the protein, and the second entry of each tuple is the actual amino acid sequence. In our example here, we only have a single protein amino acid sequence, but further down you will also see an example where we will use multiple amino acid sequences in the same batch. Here we have a batch size of only 1. We use the batch converter to convert our amino acid sequence to token IDs, and we see that we get a sequence of token IDs. The first token has the token ID 0, and if we remember from above, this is the classification token. The last one has token ID 2, and if you look it up above, you will see that this is the end of sequence token. In between, we have 5 different token IDs representing the 5 different amino acids in our short protein amino acid sequence. Now we want to run the model and actually get the representations. So let's do this. We see that as the outputs we get logits which predict each position in the sequence and as a result of the masked language modeling training. And we also get representations from the last layer, in our case the 6th layer, which is what we're actually interested in. So let's have a closer look at the representations from our last layer. We see that they have a shape of 1, 7, 320. The 1 refers to the batch size because we only have 1 sequence in our batch. Then we have the sequence length, in our case 7 because we have 2 special tokens plus our 5 amino acid tokens. And then we have 320, which is the hidden dimension of the protein or amino acid representations. Here it is only 320 because we use the smallest model. But for example, if you use the larger model with 650 million learnable parameters, this will be equal to 1280. Now we want to have a single representation for our whole protein amino acid sequence. And we have seen in a previous video that we can compute the element-wise mean of all amino acid embeddings to get a single protein representation of fixed length. So what we do is, we take the first sequence in our batch, we exclude the classification token at position 0 and the end of sequence token at the last position, and we take all amino acid embeddings in between. And then we compute the element-wise mean. We see this results in a single vector for our protein sequence of length 320. Here I've put all steps together into a single function where we can input the sequence, our model, and the batch converter, and this gives us, for the given sequence, the resulting protein ESM-2 embedding. Now, let us have a look at how we can fine-tune a pre-trained ESM-2 model. We first load all the necessary packages and define a function for computing the coefficient of determination R² to monitor the performance of our model. We now want to fine-tune the ESM-2 model for a protein property prediction task. For this, we use a dataset published by Gado et al. That contains optimal pH values for protein amino acid sequences. Optimal here refers to the pH value at which the enzymes have the highest catalytic rate. You find a link to the original publication and to the data in this Jupyter notebook. From this dataset, we extract the training sequences and the corresponding optimal pH values. We then normalize all target values so that they are approximately Gaussian distributed with mean 0 and standard deviation of 1. We choose a batch size of 4. You might need to adjust this depending on the RAM and capabilities of the device on which you're running the code. We create a custom dataset that returns for each data point the sequence and its optimal pH value. Now we're going to load the model that we want to fine-tune. In this case, we again load the pre-trained ESM-2 model with 8 million parameters. We also load the batch converter, put the model into training mode, and obtain the number of layers and the embedding dimension, which in our case is 320. Next, we will put a prediction head on top of our ESM-2 model. We will use a single layer fully connected neural network or multi-layer perceptron with a hidden dimension of 128. We say that we want to fine-tune the model for 3 epochs. And here you see an example of how we can create batches that contain more than just one sequence. We now define our model, which we call ESM-FFN, for ESM feedforward network. This class takes as input the ESM-2 model that we want to fine-tune. Then we define a multi-layer perceptron or fully connected neural network with one hidden layer and a ReLU activation function in the hidden layer. Below you will see that this is our prediction head that we put on top of the updated ESM-2 classification token. The network will output a single value, which is the prediction for the optimal pH value. In the forward pass, we first obtain the representation from the ESM-2 model. We then extract the classification token, which we know is at position 0. Alternatively, we could also compute the element-wise mean of all amino acid token embeddings. Typically, this gives quite similar results compared to using the classification token. We then use our multi-layer perceptron to map this classification embedding to a single value with our prediction head. Optionally, I also added the function for extracting representations. Once the model is fine-tuned and we want to access the task-specific fine-tuned ESM-2 representations, we can use this function to get the updated fine-tuned classification token representations for given protein amino acid sequences. Now we will look at the code for fine-tuning the model. Again, we choose the device that we want to use and initialize the model. We use the mean squared error as the loss function, and we use the Atom optimizer to update the parameters of the ESM-2 model and of the prediction head on top of it. We then implement a standard training loop. We make sure our model is in training mode. We iterate over all sequences in our training dataset, convert them into batches, run them through the model, and then update the parameters. First, we compute the loss function, then we perform the optimizer step. We keep track of the training losses, and after each epoch, we print the training loss, which is the mean squared error. Then we run a validation loop where we go through all samples in the validation datasets. Afterwards, we compute and track the mean squared error and the R2 values, and we print them. Below you can see the results for the code that I already executed. On my laptop, each epoch took approximately 45 minutes. You can see that the loss function is going down and that the performance is improving, and we would probably get even better results if we continue training. Below that, you also see the performance on the test set. The fact that this loss or this test loss is lower than the validation loss is due to the fact that the validation set was designed to only store sequences that are very dissimilar from the training set, and hence it is more difficult to predict the optimal pH for these enzymes. Hopefully this video gave you a good idea of how to use and fine-tune the ESM-2 model.